So you'll notice that up to this point, we have used a sample of one person to make a decision in my hypothesis test. I had the whole population. I knew it was conveniently following a normal distribution. And then I took one person as a sample value and used that person's score or result to make a decision about the whole population. Now, in general, that might not be the best idea because when I pick just one person from the population, I could get an extreme value. That person might not be representative of the whole population. So what would make more sense is to select a sample of individuals and look at the average score among those sample values and use that average to compare, that mean, that sample mean, to compare that to the population mean. Because the larger my sample, if it's selected well, the more representative it will be of the population as a whole. So comparing the sample mean with the population mean might give me stronger evidence to support my research hypothesis, whatever that may be. So instead of selecting an individual sample value and hoping I don't get something, or hoping that I get something extreme, well, the chances of that might not be so great. But if I have a sample of, let's say, 2 individuals, what are the chances of getting 2 of them that extreme? If I do get that, then that's much stronger evidence. For example, if we go back to the intelligence example, where in the stadium she selects just one person, yes, that person might have above average intelligence. But if I force her to select 2 people, and if she selects 2 people, and both of them are above average, then the evidence is much stronger that she has some ability. And what if I make it a larger sample? If she selects 10 people, and their average intelligence is higher than average, then the evidence is much stronger, much stronger. She could have gotten lucky with 1 person, but with 10, not as easily. So using a sample instead of just one, a sample of more than one value instead of just one, and comparing the sample mean to the population mean, instead of just a single sample value, that will give me stronger evidence, more confidence in my hypothesis testing. Okay, so let me just see what I want to say. So in order for us to, just check your slide around. In order for us to be able to compare the sample mean value, I have to know something about how those sample means are distributed. If I just take a sample of 1 person, then their score fits in this normal distribution because this is the distribution of all people's scores, whatever the score may represent. But if I take a sample, then I need to just make sure about how the different sample means are distributed across all possible sample means that I can get. For example, if I have my population of people, let's say, and I take samples, many different samples. Sample 1, sample 2, sample 3, and so on. And from each of these, I get, I get a mean, let's say mean 1. From this one, I get a mean value, sample mean here, all the way. I need to know how all sample means that are possible are distributed. Which sample mean is likely, which sample mean is not as likely. So we'll have to look at the distribution of means. Because now I'm comparing not an individual score with the population score. I'm comparing means with what the likely value is. And how do I know if I take a sample mean, is that extreme enough? I need to look at the distribution of all possible means, all possible averages that I can get from samples of a specific size.
What do you mean by which is likely? You were saying which sample mean is likely.
In terms of where do I decide on the cutoff? What sample mean do I have to get to decide that it's extreme enough? Or is it a likely sample mean value to get? If I take samples of, let's say, 10 people, over all possible samples that I can get, what sample mean values are considered extreme, and what sample mean values are considered common and likely to get? Just like if I select individuals.
Yeah.
Individuals with scores in this area over here are likely to be selected. There are a lot of them, but some of them are more extreme. So in order for me to know that, I have to look at the distribution of all individuals.
Yeah.
But now I'm not looking at individuals anymore. I'm looking at samples of whatever size I decide on. So I need to know if I take a sample and I get a sample mean, how likely is that to occur? Is that an extreme sample mean? Is that a common one? In order for me to do that, I have to look at how all possible means are distributed. Which ones are likely? Which ones are not likely? What is that profile? It's not the same necessarily as the distribution of the individuals. It's not the same.
Okay.
Well, it's similar, but it's not the same. Let's look at an example. So when we do the distribution of means, it might seem a little strange. But let's just look at this for a second. So what am I representing here? So I'm looking at grade levels, randomly selected from a large group of students with equal number of grades, 1 through 9. So now I'm looking at the histogram of all samples of 50, of size 50. All samples, so I get sort of a balanced frequency here if I look at samples of size 50. If I increase the sample size, then I find that the profile is going to change, and change. This is really what the central limit theorem is telling me. That the distribution of individuals can be anything. If I take small samples, then I can't really see anything. But if I take large samples and over all possible combinations of samples that I can get from the population, if the sample size increases, then the histogram profile gets closer and closer to a bell shape, a normal curve. Central limit theorem says exactly that is theoretically what is going to happen. So let me just summarize the central limit theorem here very informally. Central limit theorem. That, let's say it like this, the larger the sample size, which is an n in this case, the closer the distribution of all possible means coming from that sample size. All possible. If I say I'm looking at a sample size of 600, then across my population I take all possible samples of 600 people. All possible. There are many, many. And I look at how the means are distributed. So the larger the sample size, the closer the distribution of means. Oops, that's a little ugly, sorry. Closer the distribution of means is to normal distribution, normal curve. Just write correctly. Let's just say normal curve. And if I do experiment with this in practice, I see the histogram, which is an approximation of the distribution shape, gets closer and closer to this bell shape. Now, because it's an experiment, it's not going to be perfect, because I can't practically take all possible samples. But in theory, it gets closer and closer to a normal curve, and if I'm able to take all possible samples and a very large sample size, then it will be essentially a normal curve, exactly. So that allows me to say, okay, well, the individuals could be distributed in many ways. Could be normal, could be something weird, could be something strange, but when I look at the distribution of all the sample averages, that comes to a normal distribution. So in that sense, the normal distribution is the most important one to look at. And in some sense, the only one when I look at it like this, that everything is linked to a normal distribution in some way. In some way. So, in order for us to specify the exact distribution, we're going to need the whoops. We're going to need this distribution, this distribution's mean and standard deviation, so that I can know exactly, well, what exactly, which normal distribution exactly does the distribution of means have for whatever situation I'm looking at. Okay, so, the wrong page. Okay, so 5.2. So there are really three kinds of distributions working here. I look at my individuals, and it could be a nice normal curve, or it could be something else. It could be many things. For many variables that I investigate, it's a normal curve, but it doesn't have to be. If I look at wait times at a bank, how long people wait at a bank, for example, or at a drive-through, those are not normal distributions. Whatever this distribution is, when I look at my sample from the population, a certain number of individuals making up my sample, the histogram for that single sample is going to resemble the actual distribution. It's an approximation of it. Because I'm not looking at the whole population, only a sample, it's a little jagged. It's not exact, but it approximates it. When I look at the distribution of all sample means, that is also a normal distribution, but slightly different than the population. And in fact, this doesn't have to be normal. This could be something very different, but this is still a normal distribution. That's what the central limit theorem is telling me. So we need to be able to find the mean of this distribution on the right, and the standard deviation to know exactly what that normal curve looks like. So it's a little strange. This could be anything, but this is really, the central limit theorem really unlocks everything and allows us to do everything that we'll do from this point on in terms of the test. This could be anything. If I just look at the sample of individuals, it's trying to resemble this. But when I look at the distribution of the means across all possible samples of that size, this is just one. Then the means, the sample means, always have a normal distribution if my sample size is large enough. So for the mean, we have to give it a name. So for the mean, we'll now call it mu m. For the mean of the distribution of means. So it's the distribution of all sample averages. So every single value here is a possible sample average. The mean of that distribution in C there on the right we'll call mu m, just to distinguish it from the population mean. But the nice thing is that if I take a lot of samples and I take the average inside each sample and I take the average of that, because the averages are just adding up scores and dividing them by how many there are, the average of those averages will still be the same as the average of my population. So conveniently, the mean of the distribution of all sample averages, let's say, is the same as the population mean. So let's say the same as population mean. It's the same. Because of how I calculate an average. I just add them up and divide by how many there are. If I do that in groups and then average out the groups, it's still the same. It's still the same. So that's nice and convenient. And I mean, technically these things are have to be proven from the theoretical equation describing this shape. And you have to derive these things and all that. I'm just trying to get an intuitive understanding. And sometimes it's hard to do. So it works out well that the means are the same. And so that means that, that implies that the position of the center is the same as this one. But the variance is not quite the same. Variance is not quite the same. So let's at least try and get a little bit of intuition for why I claim that the variance is going to be less. When I take a sample of 2 or more individuals, the variance is going to be smaller than just the one, if I just take one individual. And the more I take, I'm not going to see a lot of extreme values. I might see some, but the larger samples I take, the more balanced it'll be. If I just take 2 people in a sample, I could get 2 extreme values and then the variance is going to be high. But if I take more people in my sample, then it'll balance out a little more because it's very unlikely that I'll get all of them extreme scores. That's not going to happen. It's too unlikely. So the larger my samples, the smaller the variance is going to become because it's going to be spread out and balanced a little bit more. So the rule is that the variance for my distribution on the right there, the distribution of sample averages, I'll say, sample means, is, we'll call it sigma squared with a little m to indicate that it's the distribution of means, not the distribution of individuals in my population. And the rule that is derived from the theoretical equations is that I have to calculate the variance of the distribution of means, I take the population variance and divide it by the sample size. So the bigger my sample size, the less variance I'll see. So those guys, it's not that bad to remember. This has no adjustment, this has a little adjustment. So this is why the graph on the right is much narrower. It has much less variance than the population distribution. So why exactly it's an n? Well, you have to derive that theoretically, but hopefully you have an intuitive understanding that yes, if I have a bigger sample size, because then I get a more balanced set of individuals in my sample, the variance is going to go down in that sample. All right, so 5 point. Any questions so far? So I'm looking at a sample of not just one person like we've done in the first part of our introduction to hypothesis testing. I'm just looking at one individual because I could get an extreme individual and then accept my research or reject my null hypothesis in support of the research hypothesis. When I'm basing it on one person in the population, maybe it's a little safer to look at a collection of people, a fairly large sample. Base my decision on what the sample average is. But then I have to look at how that sample average sits among all possible sample averages. Is that a likely sample average? Is it not? How does it compare to the distribution of all sample averages? We're happy with the idea of what we're doing. We fill in the detail as we go. Just the idea of now I'm switching from the individuals to sample averages, sample means, and looking at all possible sample means. And regardless of the individual population distribution, the sample mean distribution will always be a normal distribution if my sample size is big enough. So 5.3. So if I have to calculate the variance, I take the population variance and divide it by the sample size, the number of each sample. For example, if let me leave the formula up there. If my population variance is, let's say, 12, just picking nice numbers, then depending on the sample size, the variance for the distribution of means will be different. If I have a sample size of 2 people, 2 individuals, then it will be 12 divided by 2. Let's call this the variance of means, the 6. If I have a sample size of 3, then it's 12 divided by 3. 12 divided by 4, 12 divided by the size of the sample. So it changes. And the bigger sample I get, the more balanced it is, the more representative of the population. And I'm not going to see much variance among them because they represent the population. If I have a population of, let's say, let's just go extreme, and I look at that stadium example. Let's say the population, that's the population, and it's 100,000 people. If I take samples of 99,000 people, all possible 99,000 people, that is so representative of the whole stadium, I'm not going to see much difference between those samples. The variance is going to be extremely low. There is no variability. There's no real difference between them. But if I take just 10 people, all possible samples, there are many, many samples, of 10 people out of the stadium, I can get many different results inside each sample. And there is some variance. There's some variety in what I'll get, the variance will be much bigger. Another example here, if my population variance is 50, then depending on the sample size, I divide the population variance by the sample size, and the larger sample size will result in a smaller variance, smaller fluctuations between the samples. There isn't much that I can get in terms of variability if my sample is big, because it becomes more and more representative of the population. So I'm not going to see much difference because each sample represents the population so well. With large samples, I represent the population much better. So what slide is this? So if I then, of course, want the standard deviation instead, I'll name that appropriately to just a sigma m. M indicates the sample, the distribution of means. Standard deviation of that is then simply the square root of square root of the variance, or I can rewrite this as the population standard deviation over the square root of the sample size. So these are linked in the obvious way, but I want to talk about standard deviation instead, like we have up to this point, talking about standard deviation steps and getting the z-scores and all those things. We're going to get back to that. But if I have the variance, then I can easily get the standard deviation. So in this example, we calculate the variance and then simply take the square root of that, or you can also just do it like this, depending on the information that you have of your population of individuals. So that was 5.4. So this guy is also called the standard error of means. Standard error, I guess, of the mean, sorry. That's a better way to say it. Standard error of the mean, S-E-M. Standard error, or just standard error. Standard error of the mean. But it is just the standard deviation of the distribution of means. And I'll put it up here. So let me just rewrite this. That the mean of that distribution of means is the same as the population mean. So what people have found was that two things. Let's look at the shape of the distribution of means. Two things. If the population, I'll just write it like this, is normal, then the means, what is that? That's supposed to be an N. Then the means will have a normal distribution as well. If the population is not normal, meaning it doesn't have that normal curve, it could be something else, and that does occur. Wait times at a bank, drive-through, things like that, it's not a normal distribution. Not normal, then the distribution of means is still normal if my sample size is at least 30. So if I just, the central limit theorem says, bigger sample size, and regardless of what the population is doing, the distribution of means approaches a normal distribution. Where is an acceptable crossover point for the sample size? If it's at least 30, then it's close enough to a normal distribution regardless of where the population comes from. If it's less, well then I can't use this. I have to have other kinds of statistical tests that we'll get to eventually. So 30 is my cutoff. If I have a sample size of more than of 30 or more, then it really doesn't matter what the population is doing in terms of its distribution. But there is one exception if I have a population that doesn't have a normal distribution and the small sample size, well, many different things can happen. And I have to look at that differently. Any questions on this? So just remember the 30. 30. All right, 5.5. So I have my distribution of individuals. It could be normal. And the distribution of means is a normal distribution. It has the same mean, it has less variance, and it's also normal as long as either the population has a normal distribution or my sample size is at least 30. So if I just sort of go down here, let's just look at this for a second. So I have different kinds of population scenarios. And suppose I have a mean of 109, variance of 400 for my population, therefore a standard deviation of 20, but I don't have a normal shape for the population. If my sample is, whoops, that's not what I want to do. Let's go back. If my sample is 100, it doesn't matter. The distribution of means will be normal, and I calculate the new mean as the same, the means are the same, and the standard error of the mean, standard deviation of the distribution of means, I calculate from the population standard deviation. If I have the same situation and the population is normal, well then I'm good. It doesn't even matter what this is. It doesn't even matter what the sample size is. The distribution of the means will be normal as well. Bell curve, normal shape. If in the third case here I don't have a normal distribution for the population and my sample size is too small, less than 30, then you can calculate these guys, but it's not a normal curve anymore. The distribution of means is not normal, and then I have to do something else. That's the only exception. If I have a normal distribution and a small sample, it doesn't matter. Distribution of means is still normal. If I have the population that's not normal, it comes from something else. If my sample size is big enough, the distribution of means will be a normal, will have a normal shape. Any questions on that? This just summarizes that again. So I have to remember, of course, how do I calculate the sample values? The population parameters have to be Greek letters, and the distribution of means, all possible means, will be calculated from these, with no adjustment with the mean and a little adjustment with the standard deviation. And we call this guy the standard error of the mean. All right, so the only difference now between the hypothesis testing that we did before with the one that we're doing now is we're going to look at the sample mean. and see how does that sit with all the possible sample means that I could get of that size, and should I consider that to be an extreme value? Does it support the research hypothesis? What do I do with it? So how does it fit with the distribution? And that's why I need to look at the distribution of all the sample means instead. And that one is always going to be normal as long as either the population is normal or my sample size is big enough. It's not even that big. 30? That's not that big. So it's going to be normal very quickly. The means are the same as the population mean, and the standard error of the mean, it just has a little adjustment using the sample size. All right, so the procedure is exactly the same, but in order for me to get the z-score, I would have to, of course, use the mean and the standard deviation for this distribution. This is now the distribution that I use for comparison, the distribution of means. So now to get a z-score, I would have to use my actual sample mean value that I get, and I'll call that m for sample mean. And x refers to an individual score. I'm now taking a sample, looking at that mean, where that sits in the distribution of means. So it's going to be the specific sample mean that I get minus the mean for that distribution over the standard deviation for that distribution. So I have to use the distribution in question, which is now the distribution of means. That's really the only thing. So if we go to our example, our familiar examples, sort of. The stress reduction example, where I am now taking a sample of 20 individuals to see if the treatment or the program to reduce stress had any effect. So my population is the people trained in the stress reduction method, and I compare that with the general population, those not trained. And I'm trying to see if there is a reduction in stress. So if population 1, with the method applied, will have a lower average stress, a lower mean compared to the general population. And the null hypothesis is then the opposite. No, it has no effect. So now I am looking at what I have to work with. So I have a sample of 20, and I find that the sample mean is 25. And I'm going to compare that to the general population mean of 40, standard deviation of 10, and the individual distribution. And it has a normal shape. So if it's normal, the sample size of 20 doesn't matter. The distribution of means will be normal. So I don't have to worry about that. So I need to look at the distribution of means in terms of what is its mean. Well, it's the same. It's 40 again. It's the same as the individual population mean. And the standard error is going to be, it doesn't matter which formula you use. You can calculate the variance first, take the square root of that, or you can use the individual distribution's standard deviation and divide it by the square root of n. Either way, you get 2.24 as the standard error. So it's less than the individual distribution. There's less variance, there's less deviation from the mean. And the shape is normal because the population is normal. So now I have to determine my cutoff. So let's maybe make a little graph here to visualize what's happening. So even though the distribution of mean has a narrower normal curve, I'll still spread it out so I can visualize it in a more convenient way. So this is now where the mean sits. This is now the distribution of means. So this is mu m, which is 40. And I'm deciding on a cutoff. Let's suppose I'm looking at a 1% significance level. So what kind of test is it? Is it a one-tailed or a two-tailed test? Well, for that I need to look at the statement of the research hypothesis. Would you say it's a one-tailed or a two-tailed test? One, because I'm only interested in looking at if the mean is less than the population 1 mean. So I'm going to have a cutoff here somewhere that I'll exaggerate so that this over here is 1%. Now what is the z-score that gives me that? Well, let's go to my table and look. I have, so I'm looking at it on the left, but because of symmetry, I can look at it on the right. Find the z-score here first, and then just flip it around to make it negative. So I'm still looking at the percentage in the tail, and I'm looking at a 0.01 or 1%. 1%, or I'm going to have to page a little bit for that. It's going to be out there. 1%, 1%. Page 676, 1%, 1%. Let me say here what I get. Z value and the percentage. Where is it now? I get a 1.02. which corresponds to a Z value of 2.32, and I get a 0.99, so less than 1%, 2.33. Now you can do different things at this stage. They pay. Or it doesn't matter. Where is it? Am I just missing it? 2.33. So in this case, you can pick something in the middle, but to make it simpler, you can argue that, well, this second one is closer to the 1% line, so we can just pick that one. There are different things you can do at this stage. I'm happy with either one. Some interpolation technique, picking a number in between, or just picking the closest one is fine. So, oops, that's on the other side, isn't it? It's on the other side. 2.33, so then my Z value in question will simply be negative 2.33. That's what this says over here. So that's my sort of my critical value, my critical score, and I'm going to compare what my sample is doing. Which side of this line is it sitting? And what does that tell me in terms of my hypothesis? So now I look at my sample, and my sample size is 20. I look at the corresponding Z-score for this distribution of means. So I'm going to calculate the sample mean, compare it to the distribution's mean with the standard error, because that's the standard deviation for this distribution. And I get a Z-score that is really small, really, really low. I'll do it in another color. Let's go with red. So z-score sits somewhere over here. Negative 6.7. 70 if you want. So what does that tell me? It's right there. It's less than the critical value. I found a sample that is very extreme in terms of its average stress score. Very extreme. I was happy with this level over here. This is much more extreme. That's very unlikely to find. If I look at all possible samples that I could take, the chances of getting something in this region over here is 1%. I get something way out there. So that is strong enough evidence to say, yes, this does lower the stress as I hoped. So I reject the null hypothesis that says it does not in support of the research hypothesis that I was hoping to be true. Any questions on that?
It almost makes you think there's an error somewhere though, that was happening.
Why do you say that?
Well, we get 0.67 maybe.
No. The chances of randomly selecting in the whole population, if the null hypothesis is true, I should have said that. If the null hypothesis is true, this is the distribution under the null hypothesis. If the null hypothesis is true, and there's no effect, then the chance of getting some sample with mean in this area over here is 1%. So the only way, realistically, that I would get something over here is if there's an actual shift towards that side, because it is so unlikely to just randomly get it if there was no effect in the treatment. So yes, I should say, this distribution applies to the null hypothesis being true. If the null hypothesis is true, then randomly selecting a sample among all possible samples, there's a 1% chance of getting something in here. So if I do get something in here, that is so unlikely that I have to conclude that the null hypothesis wasn't true. And there's actually a whole shift towards a reduced stress. Does that make sense? Let's see if there's a sketch in there. No, there is not. All right. Any questions on the stress exam? Okay, so one more example where we do a study where people are told about a person in terms of their positive personality qualities, and then they meet the person and rate the person's attractiveness. So population 1 has been given information about the person before they meet the person, and population 2 has no prior knowledge of the person. And we're trying to investigate if that information changes your opinion of the person in terms of attractiveness. So the research hypothesis is what I sort of suspect and hope to conclude, that the attractiveness score from the first group of people is higher than the second group of people. First group of people having information about the person before they met the person, second group of people no information. That population 1 gives the person a higher attractiveness score than the rest of the population, or the population 2. And the null hypothesis then is that there is no increase in the attractiveness score. So now I have my null hypothesis and my research hypothesis, and again I am looking for, and I'm hoping for, an increase in the mean. So I have a one-tailed test again. And I'm gonna have my cutoff value somewhere according to what I decide. Let's suppose I decide this time on 5%. So the setup is gonna be like this. But I have to calculate, okay, so I'm gonna take, for example, a sample of 64 people to see what the average attractiveness rating is among those people in my sample. And I get a sample mean of 220. Now the population mean is 200 with a standard deviation of 48, and the shape is something else. Doesn't have a name, something strange, not normal. But because my sample size is big enough, it doesn't matter. When I look at the distribution of means, that is going to be a normal shape because I have 30 or more people in my sample. So I calculate the mean. The mean is the same. Standard error, I get a 6, less than the population 2 standard deviation. And the shape is normal because I have at least 30 individuals in my sample. So I decide on my significance level. Let's do a 5% this time. And if I look up, let's just double check that I get the right value from my table, the right score. I'm looking for 5% in the right tail. That fits nicely with what my table shows. I'm looking for 5%, page 675. 5%. Now here's where there are different opinions in terms of exactly which z-score to take. If I look at the 5%, where was this now? 5.05, 1.64 for a z-score, 4.95, 1.65. So some folks would, like this, pick the 1.64 level. 1.64. Some could argue that it's exactly halfway between, so why don't I pick the halfway mark? Just to be consistent with the slides, I'll pick 1.64. I would personally pick the halfway point between them because the percentages are exactly between them. But there are different ways. You could do other techniques here as well. So not to get caught up in that, let's just stick to the 1.64. They're all giving me a number that's close. All those numbers will be close. And to be honest, if my sample mean sits right next to this line, then maybe get another sample or continue the study. I'd like it to be either into this region or not at all. If it's on the line, then you'd have to investigate it a little bit further. So I'm hoping it doesn't really, if I pick 1.645 or 1.65, it shouldn't make much of a difference because my sample is not going to be that close to this line. So it's not really something to obsess about. Okay, so now I look at my sample and what it's saying and how it's sitting in relation to the distribution of population 2, right? If the null hypothesis is true, then I have a 5% chance of getting something this extreme, past this Z value, this score. All right, so my sample is 64, mean of 220. I convert that to the corresponding Z score. 220 minus the distribution mean divided by the standard error, the standard deviation of this distribution. And I get a value of 3.33. That's marked in red. Red's not great, but 3.33. What does that tell me? That tells me that the research hypothesis is probably true because the chances of finding something this extreme, if the null hypothesis were true, is pretty unlikely. So it's evidence at the 5% significance level to support the research hypothesis that there has been some sort of shift in the distribution. Any questions on that? So I reject the null hypothesis in support of the research hypothesis that there is some change. The mean is higher. Any questions? Makes sense? You can start to notice, hopefully, that it's the same thing over and over. Visualizing it helps. Same thing over and over. So, slide is this? 5, 10. So really, regardless of the population distribution, whether it's normal or not, if my sample size is big enough, I get the distribution of means, and my sample is going to give me a sample mean, which puts me either in the what I consider an extreme case, and that gives me evidence to say that no, there was a shift in the properties of the population, because that kind of sample is too unlikely to just get by chance. All right, the last thing that I want to talk about is confidence intervals. So I have this standard error, and then I want to say, in addition to the hypothesis test, I want to say where the sample mean is. But I don't know for sure. I have a sample and a level of confidence. And the level of confidence will sort of prescribe a range of values. And I'll be, for example, 95% confident that the new mean sits inside that interval. Of course, the larger I want my confidence percentage, let's say my confidence level, if I want 99% confident, then I have to increase my interval to make sure that the mean, the new mean after the treatment, whatever kind, that it sits in that interval. If I'm only 95%, if I only require a 95% confidence to capture the mean, then I can have a smaller interval. If, for example, I only require 80% chance of capturing the mean in my interval, then my interval doesn't have to be that big, because there's a 20% chance that I'm missing the interval. So it depends on the confidence interval. And how we calculate that is with the z value times the standard deviation, the standard error of the mean, plus and minus that distance from the mean. And then I can say, well, there is a, when you look at the graph here, can you help us? There is a 95% confidence level that I'm capturing the mean, the new mean, using my z value, and I can decide where my percentage, what my percentage should be. If I'm 95%, if I want to be 95% confident, then I want the area here to be 95%, and the z value tells me where how far do I go up and how far do I go down to cover 95% of the possibilities. If I want to be 99% sure, then the corresponding Z value that I've gotten here in the hypothesis test is a little bit bigger. I have to extend my range so that I cover more possibilities and lower the chances that the mean is outside of my interval. So I just want us to be aware of the idea of a confidence interval in addition to the hypothesis test. I use the same Z value and just cover the distance from the center to cover the corresponding percentage, and then I can say, okay, I'm 95% sure that the new mean will be covered in that interval. If I want to be more confident in containing the mean, then I have to stretch that a little bit to cover the corresponding percentage and be sure that the mean, I'm not sure exactly where it is, not sure exactly because my sample is only one value. My sample could be a little off from what the new population mean actually is. So I'm going to use my sample and then give myself a little bit of room to say, okay, based on my sample, up and down a little distance, and I'm fairly certain that I've captured the actual mean in that interval. I can't say that the actual mean is the same as my sample mean, because this is just one example. So I give myself a little bit of room in either direction to be more confident that the mean is, the actual mean sits somewhere in here. It might be very close to my sample mean, but it might not. I want to give myself a little bit of room. All right. Any questions on using the means, the sample means, instead of a single individual to sort of improve on the hypothesis? Yes.
All right, hello. I just wanted to add a little bit regarding confidence intervals, just in case the previous bit wasn't perfectly clear. When I think about confidence intervals, I really think about something that's not integrated into the hypothesis test procedure, but it's more running parallel to it, doing something similar but separate, getting to the same conclusion. The best way to look at it is just by a little example, and the process is pretty much always the same. So let's focus on the personality attractiveness example once again, where I had a sample of 64 people, and that gave me a sample mean of 220. That I'm now essentially comparing against my population mean of 200 to see if there is a significant increase, or if the sample suggests a change, a shift in population 1. And I also got the standard deviation when I look at the distribution of means to be 6. So when I talk about a 95% confidence interval, we're mainly going to focus on 95%. We want to establish a range of values, an interval, around my sample mean so that it contains the true population 1 mean 95% of the time. With 95% confidence, I'm trying to capture the mean. Now, I don't know what population 1's mean is, what the new population mean is. My sample is a suggestion, but it might be not completely accurate. That's all I can go on. So I want to have a range of values, an interval, so that I'm fairly confident, fairly sure that I've captured the mean, and it's somewhere in there. I don't know exactly where. Now, what do I mean by this? Well, if I look at my diagram here, my population 1's mean is now essentially estimated by the sample mean. And I want to construct an interval around it, find 2 points, one to the left and one to the right, so that 95% of the possible values that I'll get fall between these two values. In other words, the probability of finding a value is 95% and then 2.5% in either tail, of course. So the probability that I'll fall between negative z and positive z should be 95%. But now I'm working with my distribution, so I have my sample mean here. I'm working with the standardized distribution. I have my sample value here, so I want to standardize that to the corresponding z value, z score. So I subtract the mean and divide by the standard deviation. Now if I simplify this a little bit by multiplying throughout by sigma m, I'll get this inequality, and this is really two inequalities in one, just written down like this for convenience. I have the one inequality here giving me one side, that on the left, and the other inequality here for the other side of the interval. So then I simply have to add m on both sides for each of the inequalities, or throughout essentially, and I'll get that the equivalent statement here, that I'm looking for the probability that wherever the true mean is, I want the corresponding z-score to be between these two values. Now x bar here, I should say, is the true mean of the population, and m is my sample mean. So I want the probability that the population mean falls between these two values, to be 95%. Now 95%, when I look at my diagram, would correspond to a z-score of plus and minus 1.96, like we've seen before. So if I want to have a 95% probability of getting the population mean between these two values, I'll have to have a z value of 1.96. So when I calculate these using my m, my sample mean, and my standard deviation, I put those numbers in there and I get the 95% confidence interval ranging from 208.24 to 231.76. So now I can say that there's a 95% chance that I've captured the actual true population mean here. It's somewhere in there. Maybe my sample of 220 is dead on, but probably not. It's going to be close, but I don't know exactly how accurate it is. I only have a range of values and a certain level of confidence to say that it's somewhere in here. Now how this is essentially working parallel to hypothesis testing, coming to the same conclusion, is now when I look at this, and what is hypothesis testing trying to do? It's trying to see if my sample gives me strong enough evidence to suggest that the population 1 mean is above the 200. Now this confidence interval says that at a 95% confidence or significance level, the population 1 mean is in here. But this starts at 208 and ends at 231. So this is only containing values above 200. 200 is on the left of this. This does not contain 200. So I could say that I'm 95% confident that the true population mean, which is in here, and therefore above 200. So the confidence interval path leads me to the same conclusion, that population 1 has a higher attractiveness rating based on my confidence interval. And that's again at a significance level of 95% or 5%, depending on which one you're talking about. The 95% would go with my confidence interval, and when I talk about hypothesis testing, I would use 5%. But they have the same significance level. So this is another way of going through the logic, the same as hypothesis testing is doing, but it's doing it a little bit differently. I see them as working in parallel, getting to the same conclusion. Now, of course, this is reliant on the fact that I'm using the same significance level. If I'm doing a hypothesis testing procedure with an alpha of 1% and I'm looking at a 95% confidence interval, then those two might not agree. I need to have the same significance level. So hopefully this clarifies the idea and the steps involved in calculating a confidence interval a little bit better.